Welcome, everyone. We'll get started in just a couple minutes. We'll give folks just about another minute to join, and then we'll get started. Okay. Hello, everyone, and welcome. My name is Ashley, and I work for the Linux Foundation. Today, I'm pleased to introduce Dae-Yeol Lee to present an introduction to Keystone. Before we begin, please note that the webinar will be recorded, and the slides will be available soon on the CCC website, as well as YouTube. There is a question and answer bubble at the bottom of the webinar screen. Please ask any questions you have here, and we will have time at the end of the presentation to answer them. Now I'll pass it over to Dae-Yeol to get started.
Yeah, thank you. I'm very happy to be here. My name is Dae-Yeol Lee, and I'm a PhD student at UC Berkeley. Today, I'm going to talk about an open source project called Keystone, which is now a part of a confidential computing consortium. And also, it's a project that I've been working throughout my PhD as well. So let me get started. So let's first talk about what's confidential computing. The definition from the Confidential Computing Consortium is that the protection of the data in use by performing computation in hardware-based trusted execution environment. To elaborate more on that, let's talk about three states of the data. It can be categorized into data at rest and data in transit and data in use. When data is at rest, which means that it's stored in some media like hard disk drives or USB drives, it's fairly straightforward and easy to protect it by using a typical encryption. Also, when the data is being transferred from one point to another, you can still rely on encryption with popular protocols like TLS or SSL and so on. But how do you protect the data which is being actively consumed by some computing resources? Actually, you can still use encryption. There are homomorphic encryption or Garber circuit that allows you to compute on encrypted data. However, they're usually very slow. As an example, they occur more than an order of magnitude slower overhead than the same computation over the plain text. This makes a huge gap between protecting data in use and protecting data not in use, because encryption of the data is much cheaper than doing the computation over encrypted data. So trusted execution environments, or TEE, can fill this gap by combining hardware-based protection mechanisms with low-cost encryption. So it's one of the most promising solutions for protecting data in use for now. So then, what is trusted execution environment? In the traditional viewpoint of the system, the security of the system was often basically managed by the trusted operating system. For example, the Linux kernel is in charge of process isolation, resource management, and managing all these security policies. And we basically trust that the operating system will do the right thing. So any application on top of the operating system must trust the OS. But we started to think that this might be not be a good idea because the operating system is getting bigger and bigger. And if you see the Linux kernel, it's a few tens of billions of lines of code, and it's getting bigger every day. And we may never make it entirely bug-free or vulnerability-free. Because of that, a malicious application can compromise the operating system to attack another application running on the same shared operating system. Also, sometimes the operating system itself can be compromised. Itself can be malicious, and it can hack into the sensitive applications. So this is where TEE comes into play. The idea is that by relying on a trusted hardware instead of the operating system, and the hardware guarantees that the application resides in an isolated or sometimes even encrypted memory space, often referred to as an enclave. And this isolation provides confidentiality and integrity of the specific application. And also, TEE often is backed by a cryptographic process called remote attestation, using which can verify the application's initial state and then verify that the application is running on a trusted hardware by using chain of trust based on the hardware. So the key idea here is to reduce the size of the trusted computing base, or TCB, to apply stronger security mechanisms based on the hardware. So despite of this simple idea, building TEE isn't that simple. As a hardware manufacturer, you may need to design and build the root of trust, like the crypto IP or key storage or so on. Hardware mechanisms such as in order to implement the memory isolation, encryption. Also, you may need to implement some firmware, or in this case, microcode, to allow the software to use the hardware mechanisms. This is not the end of the story. You may also need to verify the entire stack together with rigorous testing, or ideally with formal methods. Also, in order to seamlessly deploy these existing applications to TEE, you'll probably need a lot of software tools like SDK, libraries. There are actually a lot of open source projects on the software side. For example, Google's Astilo for Intel SGX, OpTEE for TrustZone, ARM TrustZone, and Graphene for Intel SGX, and so on. And a lot of them are already a part of Confidential Computing Consortium as well. However, one thing that you may notice is that there are only a few open source projects on the hardware side. I'll talk more about it. So if you think that you want to build a custom TEE of your taste, so now all the major hardware vendors have added some TEE capability to their processors. For example, Intel SGX or TDX or ARM TrustZone or AMD SCV and so on. But if you were to build a custom TEE, you cannot use any of these vendor TEE, because these implementations on these platforms are not open source. This is simply because they don't disclose their hardware or microcode or firmware. Actually, this is totally fine if you're a software developer and you're gonna just purchase their vendor like hardware and then deploy your program in existing TEE. But the caveat is that your TEE might be tightly coupled with their chips, often tied with their business as well. In other words, the TEE might have a very specific frame model and very specific set of feature, and have a lot of assumptions on software you're going to run. For example, Intel SGX, since Intel processors are usually for desktop and server machines, Intel SGX targets usually a partition server desktop applications and has a strong frame model against the untrusted external memory. And there's a lot of trade-offs for this kind of additional protection and so on so forth. So if you have any needs beyond these use cases or have different assumptions on your application, you may need a significant workaround in software side, or you may need to build the entire TEE capable hardware from the scratch. So as you notice, this is very expensive, because then you will need to build and design everything from the scratch, including the root of trust, hardware mechanisms and the microcode, firmware, and the toolings and so on. Also, you need to test and verify functionality and security as well. So to address this problem, we came up with this idea of customizable TEE, which is a concept very similar to software-defined network. So the key idea here is that you can build your own hardware, and then you can customize the TEE by using a software framework. The framework will provide the building blocks of TEE in software, including the common base, which includes the basic features of the TEE, like the memory isolation and attestation. And the thread model, like you can configure thread model and features at the compilation time, and then they can generate a TEE firmware that has these features that you have customized. And then the framework is in charge of assembling the building blocks based on the hardware configuration and generate the specific implementation, which is compatible with multiple hardware. So we started the Keystone project. As I mentioned in the previous slide, Keystone is a framework for trusted execution environments. It's an open source project with permissive licenses. The first version was released in December 2018. It's based on a RISC-V instruction set architecture. I'm going to talk about it a little bit more later. Keystone was started in University of California, Berkeley as an academic project. So there's an academic paper as well, published in last April. The paper also contains the reasonings behind our design decisions and then the evaluation on multiple benchmarks. So if you're interested, you can check it out. So here are the goals of the Keystone project. First, we want to enable TEE on every RISC-V processors for free. We enable that by following the RISC-V standard ISA and sub-ISA as much as possible to provide a basic set of TEE functionality, as I mentioned, such as memory isolation and attestation. And then on top of that, we make TEE easy to customize depending on specific thread model or specific needs. People can still add platform-specific feature, like, for example, cache directional defense or memory encryption by just reconfiguring your firmware. A key idea here is that you can easily reuse a specific part of TEE implementation across multiple hardware platforms, and any hardware creator can easily extend our implementation to enable their custom TEE with their own hardware and also contribute back if they want. Most importantly, we'd like to reduce the cost of TEE development. We believe that every processor in the world will have some type of TEE in the future, and a lot of applications will rely on TEE. So anyone who wants to build their own chip or customize their own TEE should be able to enable it with very, very low cost. So in order to do that, we're working on reducing various costs, such as hardware integration and verification and so on. This is kind of work in progress of our project. So before we dive into the technical details, I'll introduce RISC-V. I'll talk briefly about RISC-V. So RISC-V is an open instruction set architecture. Note that this is not an open source processor, it's an ISA. And the key design philosophy of the ISA is simplicity, efficiency, and extensibility. So it fits our project perfectly well. It's now becoming a kind of industry standard ISA for all kind of computing devices, starting from the embedded devices and then server devices. RISC-V ecosystem is also growing rapidly on both software and hardware side. There are a lot of like open source and commercial RISC-V cores available out there. And more companies are getting involved in this area and building their own RISC-V chips. A lot of microcontrollers or embedded devices are already being built with RISC-V, and we're expecting very high performance server class RISC-V processor in 2 or 3, maybe 2 or 3, hopefully a few years. So how do we implement TEE in RISC-V? So I'll talk about it by comparing the x86 and the RISC-V. So here's the difference between x86 and RISC-V privilege levels. In x86, kernel is running in ring 0 privilege, and both user process and kernel will interact with the hardware using x86 instructions. And these instructions are executed once translated in the hardware to a microcode, and the hardware microarchitecture will run this microcode. So usually what we do in order to implement TEE in this RISC architecture is to implement them in the microcode layer. So for example, Intel Asterisk, most of the features are basically implemented as a instruction, CISC instruction, and it's basically implemented in the microcode. In RISC-V, however, since it's a RISC architecture, there are currently 3 software privilege modes: user mode, which is U mode, and the kernel privilege, which is supervisor mode, or S mode, and then the machine mode, which is corresponding to the microcode in CISC architecture. But here, the difference is that the both M mode and S mode share exactly the same instruction set architecture. So they share the same programming language. For example, you can program the M mode firmware in a way that you would program S mode kernel in C or assembly. Also, instead of adding instructions for the TEE, RISC-V M mode can provide a interface called SBI. It's an abbreviation of supervisor binary interface, to allow S mode program to interact with the M mode. So it's a perfect fit for our project. So RISC-V TEEs are implemented via the M mode software and the microarchitecture feature. So implement Keystone as a part of M mode firmware with RISC-V Open SBI firmware library. Basically, it is you can think of it as a non-standard extension of RISC-V SBI that allows the supervisor to manage the enclaves. So before I move on, I will check some of the questions. Okay. Yeah, I'll answer them. Let's discuss this after the talk, since it seems there are many open questions. This is overall architecture and trust model of Keystone. So Keystone requires a trusted hardware with unmodified RISC-V cores. It must be a standard RISC-V core, and then the root of trust, and also some optional hardware such as cache controller, advanced cache controller, or cryptographic accelerator like the AES accelerator or HMAC accelerator, and so on. And on top of that, the security monitor will run in an N mode. The monitor implements the basic security features such as memory isolation and manifestation, and is in charge of providing a proper abstraction and interface of the hardware. So for example, the security monitor should work with different kinds of hardware, but should provide the same interface to the upper layer software. On top of that, there's a traditional operating system and legacy application running on top of that. And then the host, I'll call these legacy stack host. And the host can launch and execute enclaves by calling the monitor using the SBI interface. And each enclave will be isolated execution environment protected by the hardware and consists of 2 components: enclave application, which runs in user mode, and the runtime, which runs in kernel mode. I want to highlight that unlike other TEEs, our Keystone enclaves have this supervisor mode component, which is similar to a small kernel, but it's not necessarily need to contain all the features that normal kernel have. So it's very small, tiny runtime, and you can create as many enclaves as you want, and each of them will be individual isolated execution environment. So here's an example hardware deployment of the TEE of the Keystone. So if you were to build a hardware and you want to follow for example, OpenTitan security specification, you can configure the hardware in this way, where it has a coreplex. Sorry, my cat is stabbing my laptop. Sorry. You can have a standard coreplex, RISC-V coreplex The mask ROM, you can put mask ROM to have a zero-stage bootloader loaded in there, and then some device root key and signature stored in the OTP, and some additional hardware accelerator and the TR engine and timer and so on. This is just one example of the hardware deployment, but note that it's pretty simple to design a hardware that is compatible with Keystone, because it's all basically implemented in software. So let me talk about how Keystone enables the RISC-V processors. So Keystone uses hardware-enforced and software-defined memory isolation. So let me talk more about it. So we use standard RISC-V feature called physical memory protection, or PMP. So PMP is implemented by a set of special registers only accessible by the security monitor. The monitor can use a register to configure the entries of physical address ranges and the access permission to each of the range. So since PMP is enforced on every physical memory access of U-mode and S-mode software, the monitor can use it to implement memory isolation as follows. So if there's two enclaves, enclave 1 and enclave 2, the security monitor will assign one PMP entry for each of the enclave, and then one PMP entry for itself, and then configure the permission bits so that the security monitor memory or the enclave memory is inaccessible by any of the core. And then when you want to execute the code inside an enclave, you may need to enter, for example, the enclave 1. Then the security monitor will figure out which PMP entries are related, and you flip the permission bits so that the only enclave 1's memory is accessible. By using that, the enclave memory becomes exclusively accessible only when we execute the enclave code. So this is basic physical protection, memory protection. Then how the enclave can run various applications. I'll talk about how an enclave can run unmodified applications with a configurable runtime. So as I mentioned earlier, Keystone is a kernel privileged trusted component called runtime for each of the enclave. Runtime helps our logical design separation between security and functionality. We delegate most of the functionality to the runtime, while all of the security policies and enforcements goes to the security monitor. By doing this, we can make the security monitor pretty minimal and simple. Also, the runtime can be a layer of abstraction. It can implement either minimal interface and functionality for the sake of small TCB, or you could actually put a fully featured, formally verified kernel, such as SEL4, inside as a runtime, and then run SEL4 applications inside an enclave as well. Currently, runtime supports fine-grained customizability for enclave, like providing composable memory management or functionality modules in software. The details are not included in this webinar, but you can check it out in the paper or in our repo or documentation. So now I'm going to talk about some use cases for using Keystone and what are the possible use cases as well. So we've been working hard to make a Keystone multi-platform and general purpose TEE. Thanks to that, we were able to support many different hardware configurations. For example, we can support both small 32-bit addressing mode, which is RB32 sub-ISA of RISC-V, and then the 64-bit sub-ISA. Also, we can run various RISC-V cores available out there, Rocketship, Boom, or Ariane. Those are cores that we know that can run Keystone. Those are all like RISC-V standard core, and no modification was needed for those cores. We were able to run Keystone on available boards you can purchase. For example, Sci5 Unleashed and Microsemi's Polar Fireboard. And also, there are effort to run this trusted execute environment in real-time OS as well. you can check out this recent paper by Alex Thomas in published in Carve 2021, which tries to use Keystone to run enclaves in real-time operating systems. Keystone aims to generalize the interface so that it can easily support not only a partition of an application, but also you can run a full legacy application or fully featured operating system and related the application inside TEE. Also, we tried hard to make it easy to extend based on platform specific needs or available features on the platform. So few people, including us, already have shown that it is easy to extend or modify Keystone to explore the design space. They have extended Keystone to defend different threat models or improve the performance and so on. So for example, we have implemented memory encryption using the scratch pad available in the hardware, and also the simple cache partitioning using advanced cache controller available in the hardware. A group of people have also extended Keystone to improve performance by using available crypto accelerators in the hardware, like the AES or ED25519 accelerator. There are other a lot of academic users. Enclave was trying to modify and extend Keystone to they came up with this brilliant idea of having a memory sharing model for the TEE to reduce the performance overhead for some type of workloads. And they have experimented with their design on top of Keystone, and it was published paper. And there's another paper, OPAM. They use Keystone to explore the vulnerabilities in existing TEEs, and then they have prototyped their mitigation in Keystone, and yeah, show their ideas. So this shows that Keystone is already being actively used in academia, although it's not yet being used in the industry. So it's in the stage where people are experimenting with the platform and trying to contribute back to the project. So how you can contribute back to the Keystone? I'm gonna go over some key repositories that we have. Everything is in the Keystone Enclave organization, and then there are several repositories that you may wanna focus on. So there is a Keystone repo, which is a top-level repo. Usually it contains everything, every other repository as a submodule. And you can actually, if you follow our official documentation, it will let you download this Keystone repo, top-level repo, and build the entire thing with one command. There's another repository called SM. This contains the security monitor firmware generator. So you can, as I said, you can configure the available features and threat models. And then also you can configure the platform you want to run Keystone on. And it will automatically generate the firmware based on OpenSVI that supports Keystone enclaves. There's a Keystone runtime, which contains a default runtime kernel. This is very small kernel, which proxies most of the system calls and implements the memory-related system calls natively. There's a Keystone SEL4, which is modified version of SEL4 microkernel as a runtime. And there's a very, very tiny SDK, which contains useful libraries and example enclaves. And Keystone Demo, this is a simple demo word counting application with remote attestation enabled. And finally, the Linux kernel driver that proxies the user's request to the security monitor. So if you see the security monitor repository there, the directory structure is as follows. And there's a CI file. We're using Circle CI or a CI, and then the OpenSVI is a sub-module. And Plat contains the platform specific firmware code. And then the spec contains the specification of the firmware. and SRC contains all of the source files. And then we also have tests and tools. Currently, the tools only contains an Enclave hash generator. And you can see in the spec directory, you can see the specification of the security monitor. It's currently a draft version, but you can also suggest changes or add to the specification if you're going to add more SBI functions, for example. One way to quickly contribute to the project is to see what are the open issues for contribution. You can check either each of the individual repository to check what are the open issues, or you can go to this project where we collected all the tickets that is tagged with help wanted. And if you click on that one of the ticket, you can see the description of the ticket and see if you can contribute back. There are also a list of open projects. They're very, very interesting hardware and software side of the project. There is very short description, but if you're interested, you can also try to reach out us so that we can kind of discuss what we can start, how we can start. Besides from that, you can always do a bug reporting and do the feature request by using typical the GitHub issue system. So these are our wonderful contributors. So far, we have a few contributors, both from the inside of the Berkeley and outside from the Berkeley. Let's be connected. These are the related links. Forum and documentation and GitHub and website are all there. If you have any questions or you would like to discuss about the project, you can contact me directly at this email. To summarize, Keystone is an open source framework for TEE on RISC-V. And then goal of the project is to enable TEE on every processor. We'd like to make it easy to customize and reduce the cost of developing the TEE. And we are open for discussion and contribution. That was actually shorter than I expected. Let me go ahead and answer some of the questions. So Muhammad asked that the definition. Actually, can I just go ahead and answer the questions?
Absolutely, go for it.
Yeah. Okay. So Muhammad asks that the definition for TEE that you gave is specific to hardware-based TEEs. Software-based TEEs also exist. Also, you mentioned remote attestation can also do only static measurement. It can also check runtime measurement in addition to static measurement. Yeah, I totally agree with that. I think Keystone, although Keystone is focusing on the hardware based solution, they're all software-based TEEs as well. And also the remote, there are a lot of kinds of remote attestation. But the goal of the project when we started this project was to kind of have something similar to Intel SGX. That's why I started with the hardware-based TRC execution environments. But if you have, I think there's a lot of opportunity. As an open source project, there could be some opportunity to explore what's better and like what kind of remote attestation would be optimal for various cases. Yeah. Okay. So Deepak, please ask your thoughts on implications of smart NICs on the contemporary TEE architecture, especially smart NICs. Potentially being root of trust versus hardware vendor being the root of trust for TEEs. I think I need a more elaboration on this question. Can I enable the microphone to talk with Deepak? Sorry.
I believe so. Which attendee would you like to talk?
Deepak, please.
Deepak, I'm giving you access now.
Okay. Yeah. Hi, Joe.
Hi.
Yeah. Thanks for the great presentation. I think the question I asked was, one of the concern about the TEEs is you pretty much locking yourself into a hardware vendor as far as the root of trust. For example, STX, Intel, or AMD, RISC-V. And in the case of ARM as well, the ARM doesn't have a TE yet. But so that's the concern. So as opposed to, there's been a lot of discussions going on, some neutral entity being the root of trust. So I was just kind of wondering, just kind of a thought, curiosity, because the smart NICs are getting a lot of traction, and one of the value proposition is that they smart NIC being the root of trust. So can they play that role like a neutral root of trust? So instead of kind of relying on, have you thought about that, or is that maybe just may not be relevant? Yeah.
First I apologize for like not being very familiar with this smart NIC ideas. So I think to make it more clear, so by saying that you would use smart NIC as a root of trust, like what does it mean? Like you plug in the smart NIC in your machine, and so that will be
exactly, yeah. So smart NIC gets plugged in. Smart NIC gets plugged into your processor, and then using PCIe, and then it becomes part of your hardware basically. So that way, you're not relying on Intel or AMD and all that.
But how would you guarantee that your program?
I know. Yeah, I know.
Yeah, maybe so I'm not. Yeah, maybe I'm not knowing enough to answer this question, but I think still I think the idea is worth like exploring.
Well, I think smart NIC is not that important. The thing I'm kind of wanting to see if there's an opportunity to have a neutral root of trust versus one hardware vendor being. So maybe smart NIC, because it's getting a lot of traction in the resource disaggregation, storage, and compute and all that. So I thought, and one of the key property of smart NIC is being a root of trust. So I thought maybe we can leverage that as being the neutral root of trust across the TE vendors, hardware vendors.
Yeah, I think it's an idea worth exploring. Actually, there are some efforts. It's not the smart NIC, but you would have a separate like root of trust chip, which will be embedded in your board, and the board will. So this is typically how you would use a separate chip as a root of trust in the data centers. The chip will verify if all the nodes have the correct boot image when the machine boots, and then by that you can kind of separate this processor vendor and then this root of trust vendor. I think that's a similar idea. So you can search for the OpenTitan. So OpenTitan is a open source silicon root of trust, which will be a separate chip, but that will act as a root of trust in the existing hardware. So
it interoperates with the Keystone?
It doesn't. It's a separate project actually.
Okay.
Yeah.
But is there work going on to kind of be able to leverage the?
Yeah, we are looking into. Can you say it again? Sorry.
No, is there effort? So you mentioned that you are looking into it to see if you can use root of trust outside of the hardware vendor root of trust.
Yeah. That's definitely one of the possible directions. Okay. Because as you know, like relying on a single hardware vendor is very, very, very dangerous idea, right?
Yeah, exactly. Good. Thank you.
Yeah, we got a lot of questions from Yosif. I am hoping that I'm pronouncing it right. So how can we estimate how RISC-V adoption will impact the actual chipset market? Yeah, let me answer it live. Can you unmute Yusuf? Because I think they have multiple questions.
Hi, can you
Hi.
hear me?
Yeah, I can hear you.
Hi, Dayan. I put a few questions. For me, it's important. I'm really looking for this technology to be available like right now, because now it's the best. However, of course, it takes time for development, and I understand that. Also, it's important that you understand that the big manufacturers of chipsets, they have, let's say, a monopoly on the market right now. Not necessarily monopoly, but they have like big influence, big size of the market.
Right.
And how, I mean, I understand RISC-V. If I could use it on my computer, I would just buy it now. The question is, how can we get more exposure, or how can we make, and how can we estimate this for the next 5 years? Like how we can estimate this impact? Like, has any, I mean, I know for you, maybe you're more involved with what's going on. And maybe there's like, okay, I'm not looking for numbers, but like for something showing progress somewhere, wherever that is. I would like to see it, because that gives me inspiration as well.
Yeah, so I can answer based on what I know so far. So there are actually, the RISC-V is growing very, very fast. It's growing faster than like everybody expected. So now there are multiple companies working on RISC-V. Also, the major hardware companies like Intel or Qualcomm, they're also investing in RISC-V, and they're also researching on RISC-V processors. So I believe that there will be some like breakthrough in. This is just my guessing. Like in 5 or 3 years, I believe that there will be some kind of commercial RISC-V that can compete with the existing processors. And then if you see the software side of the RISC-V, it's really, really growing fast. You can run Fedora operating system on a RISC-V processor, and some of the workloads are actually performing better than like the other vendor hardware as well. So I do think that RISC-V will be a real thing. It's currently it's still in its early stage, but if you think about like how hardware, how chips are like how long the typical chips are take to manufacture, I think it makes sense that like within a few years you will see a lot of like RISC-V commercial hardware. Did that answer your question?
Yeah, so this answered my questions. Would be interesting. Do you mind? I will follow up with you maybe to discuss in detail.
Yeah, you can contact me if you want to discuss more about RISC-V.
It's very interesting to me, and I really need some resources, you know, like to make some estimation. To give a bigger background, I'm running a startup, and our startup is betting on this technology a lot. So that's why we need a bit of market or insight or something that we can measure to pitch investors.
I see. Yeah, we can also continue discussion after the talk through the email.
Okay. Thank you.
Yeah, thank you for your question.
Thank you.
Since I answered Deepak's and Muhammad's questions, I can first answer the new person's question. which is Mr. Tian. Is there a safe way to communicate between enclaves? Yeah, it's actually currently we have a mailbox implementation, secure mailbox. But this is for only small like message passing. If you want to implement some serious like interprocessor communication or shared memory, for example, that's not natively supported, but there are some research works that that enables this communication, safe communication. For example, the Enclave that I mentioned before, that is the exactly the paper that discussed this shared memory between enclaves, the model for the shared memory among the enclaves. Hope that answers your question. Yeah, and then Deepak raised another question. I'm thinking more in terms of trusting one particular hardware vendor versus neutral root of trust. Yeah, I think that's what we have discussed. So I'm gonna just resolve it. Muhammad, in one of your slides, you showed trust zone as a TE. In what sense would you consider trust zone as a TE? So good question. So trust zone is technically just a technology that divides your memory space into two. But if you see the recent trends, like recent work from the ARM, they're actually moving towards more of a TE, more something more look more like a TE, like trusted hypervisor. Actually, they have a remote attestation feature, and also based on the trust zone architecture, they are implementing the virtual machine isolation on top of that. That's yeah, that is very similar to like how Intel SGX isolates each of the user process. So I don't think that trust zone itself is a TE, but there are a bunch of technologies that uses trust zone as a basis of their TE isolation. So that's why I added trust zone as a TE. Hope that answers your question. Yeah, I think we can unmute Muhammad to answer a bunch of questions.
Yeah, hello, do you hear me?
Yeah, I can hear you.
Okay, thanks. Nice talk. And I was a bit confused at some point, so I just wanted to clarify these things. So firstly, starting with the last point that you mentioned. So basically ARM trust zone, that is not ARM trust zone. So that is what the name is, it's called realms. And that's not similar to SGX. That is basically the whole VM which is being encrypted, and that is in that sense not similar to SGX, which is basically a process-based, right? So it is more like the approach of Intel TDX and AMD SEV approach, where you have a full VM which is being encrypted. Anyway, so the question was, the other thing was that I was expecting that you will explain a little bit about the attestation process, how it works in Keystone. And for example, I'm thinking about which protocols do you use for the key exchange, and what kind of evidence do you provide, and what kind of, or how does the verification happen at the verifier? So can you elaborate a little bit on that?
Yeah, I can elaborate on the remote attestation first. So the remote attestation briefly works as follows. So there will be hardware root key embedded in the hardware, which is not readable by software. And then when you boot the machine, the boot, like secure boot loader, will grab this like boot image of the machine, which will be located in the first part of the DRAM, and then measure the entire image and then sign that image, the hash of the image with the secret key inside the device. So that's basically the summarized version of like how the secure boot works in Keystone. And then the bootloader also generate a key pair using key derivative function, and it provisions the key, the secret key to the security monitor and public key as well, and then also sign that with the device secret key. So at the point when the security monitor boots, it will have the measurement and signature that proves that the security monitor is the boot image is the right one that you would expect because of because the hash will match, and then the signature of the device, which tells you that the device, the trusted device, guarantees that this hash is legitimate hash computed by itself. So that's like what security monitor will have. And then after we finish booting and then launch an enclave, the enclave can request attestation to the security monitor. What the security monitor does is that the security monitor will hash this, like the entire initial state of the enclave, and then sign that measurement with with the key provision by the device, by the hardware, and then pass that report along with the security monitor report. So as a remote verifier, you will get two reports, one for verifying this enclave was initialized and was verified by the security monitor, and the other one for verifying the security monitor is the right one and was verified by the hardware. So by comparing these two reports, you'll be able to tell you're running an application on top of the security monitor you're trusting, and then that security monitor is running on top of the device you're trusting. So this verification happens afterwards, after you get all these reports, and then if there's any like mismatching in the hash or mismatching in the signature, you do not trust this enclave as a verifier. And also, if you talk about this key exchange, so the key exchange is not like a part of the enclave, part of the TEE platform. Instead, we rely on the application to choose whatever key exchange mechanism they would like to use. So what we do instead is that when you request a remote attestation, the application can choose to provide a user-specific data. You can put arbitrary data in your report, and that will be included in your measurement. So by doing that, you can actually bind any kind of data with the enclave. So one example is that you can pass in the Diffie-Hellman key parameters when you request the remote attestation, and then pass the parameters along with the attestation report to the verifier. And then the verifier can kind of use these Diffie-Hellman key parameters to construct a secure channel with the enclave. So so it's up to software, and yeah, the key exchange is mostly up to software, I would say. Does that answer your question?
Yeah, thanks. I will then follow up on you or check your paper for details. So can you also explain about the, so I've seen that you have some formal verification involved.
Oh, yeah.
So was, what I'm specifically interested is was there some was there any formal verification effort on the remote attestation itself?
No, we have not been focusing on that part.
Okay,
but
right.
Yeah, I'd be happy to see that kind of reports as well.
Sure, that's great. So one final thing, maybe what I would like to clarify is that, as far as I understand, Keystone, you have basically a software-based root of trust, right? So is that true, or do you have something in?
So it's intended to be hardware-based root of trust, but since we are not manufacturer, we only included the simulated version of this root of trust. which
Right.
is, yeah, but yeah, it's intended to use the hardware-based root of trust actually.
Right. So then in my understanding, that will be basically a software-based trusted execution environment, and the confidential computing consortium explicitly excludes such trusted execution environments from being called as confidential computing. So I was wondering if you have a concrete plan to move towards hardware-based root of trust, or is that something out of scope for your research?
I'm not sure what you mean by hardware-based TEE or software-based TEE. I don't know if there's a clear boundary on those two. But I would say Keystone is a hardware-based TEE because it relies on hardware mechanisms to implement like all of these, and it's the same for other as well. Like if you think the microcode as a software, then Intel HX is also a software-based TEE, right? So I think I don't know like what's the clear distinction, and I don't even know if there's any like consensus on like what is software-based and what is hardware-based. But I do believe that Keystone is a hardware-based TEE. You can because it relies on hardware isolation mechanisms, and then software is just enabling it to be available in the software side. Also, the root of trust will be in the hardware, not software, because hardware is protecting the key, and hardware is gonna make sure that your boot image is correct by hashing the boot image, and this is not accessible or modified by the software. Does that sound like a hardware-based TEE? Or
so as far as I know or understand, the distinction is based on whether you have root of trust which is based on software only, or whether you have a root of trust which is based on hardware plus some part of the software. So that is, to my understanding, the distinction. And from my understanding of your presentation is that you have a completely software-based root of trust. And
no, that's not true. That's not true.
Okay, so what parts of the hardware you have?
So let's talk with this example hardware deployment. Let me see. So you would have this mask ROM component in your hardware. So this blue box means the single chip. And if you're to implement the hardware-based root of trust, your zeroth stage bootloader will be in mask ROM. This is going to be a software, but it will not be accessible by any of the software, right? So it's technically it's a software, but it's a part of hardware. So it's a hardware root of trust, and you will have one-time writable memory, which will contain the device root key, and this will be also protected by the hardware, and it's not accessible by any of the privileged software, and it will be only available when the boot time at the boot time. So does that clear your?
Okay, so I will maybe take it offline, or I will read the paper and then get back to you. Thanks.
Yeah.
Thanks for the answers.
Yeah, sure. Thank you. I think we have one last question from Deepak. One other question is syscalls outside the enclave. How does syscall work outside of the Keystone TEE? Yeah, that's also a good question. So we're proxying some of the syscalls whenever possible. Like, for example, the IO syscalls are explicitly untrusted. So if the enclave wants to write to a file, what you would need is to open a file in the file system and then like pass in the data to to the file descriptor, and then the system call will take care of the rest. That's kind of like typical IO system calls. And then instead of implementing all of that inside the enclave, since we know that the IO is going to be untrusted, you can just pass in the data that enclave gives to the untrusted IO. Like I mean, just proxies the data to the untrusted host, and then we just use the Linux, the original system IO system calls available in the Linux to write to a certain file. That's one kind of design decision where we want to leave like the file encryption and everything up to the software instead of implementing that all of them natively in the TEE implementation. So if you want to encrypt the file, then you can implement that in software, and then before you write to the untrusted IO untrusted file, you can encrypt the data before you send it to the untrusted host. So that's basically our design decision. So although we are proxying these IO system calls, we actually implement very security critical memory related system calls actually inside the enclave. So those system calls will not be proxied to the outside of the enclave. For example, BRK system call, or let me see, the memory mapping, mmap. Those are handled entirely inside the enclave. Actually, this is quite different from Intel SGX. Yes. So Intel SGX, since it only allows the user privilege to be inside an enclave, to be executed inside an enclave. So they cannot proxy these system calls. So one way they have done was there's another project called Graphene that implements the user level library OS that serves these system calls, and they also do proxying for some of the system calls to the outside of the enclave. I hope that answered your question. Yeah, SCON also does that for SGX. Yeah, thank you for very great questions. I think I have answered all the questions, and thank you for joining the talk, and I hope you enjoyed the talk.
Great. Thank you very much, everyone, for attending today, and thank you, Dale, for presenting. As a reminder, the recording and slides will be soon shared on the CCC website as well as YouTube. Thanks again for joining, and enjoy the rest of your day, everyone.
Thank you. Thank you, everyone.